Test, test. Hello, good morning, good evening, good evening, good evening, everyone. Welcome to another episode of Excel Talk Show. We are going to code Wolfram language Mathematica on geometry plane curves. So let me show you my keyboards. Glove 80, fantastic. Ultimate hacking keyboard, fantastic. Nulia trackball, fantastic. And this ultimate device, this is called Svalbard. Svalbard, okay, Svalbard. Now this active, so it's connected, so it's all magnetic. Oh, I did something. Magnetic sensors, okay, Svalbard. So for each one of these devices, I have reviews on my website and on YouTube, so search for it. Now back to the screen, okay, so we let's begin. Okay, I pressed some key that started a new Emacs instance. So what happened? So close that, okay. So we're gonna code Wolfram language today, so geometry, okay, mathematics, geometry, fantastic. If you are here, say hi. If you are not here, play at 1.5 speed and jump around because I ramble all over. Hello, Turjack. Okay, mathematics, let's begin. So usually nobody is here, and that means I just gonna do my stuff, okay? Hyperbola, we introduced this subject many times. This is plane curves, a visual dictionary of spatial plane curves, a project I did since 1994. Okay, so it was the most popular website on the web throughout the 1990s and 2000s. One of the most popular math website. So linked by like over 1,000 universities. Okay, so anyway, so I'm gonna update this because many of these are 30 years old graphics. For example, this is Hyperbola, and we just updated, so this is new fresh image, but you can see as you scroll down, you'll see 30 years old images. You see, these are 30 years old images, so we're gonna redo them today, okay, that and these two, for example. Okay, so showing browser, jump to Hyperbola, open it, showing browser, okay. At the top there is .mb, that's Wolfram language notebook. Open it. So you are seeing the Wolfram language notebook source code. And here is 100 ml red wine to soothe my soul. Am I doing good? Video check, audio check. Say hi, okay? Comment. Okay, open the notebook source code, make a copy, go to the directory so you can see we got a copy, close that, go to the Wolfram language notebook. Now, is the font large enough? Yeah, kind of. We can magnify it one more. Okay, so now so this is 30 years old, but what we want to do today, let's try to do this one, okay? This is called pedo. So if you, let me explain the mathematics, okay? This is called pedo curve. Okay, so there's quite a few. Let's see, yeah, so one image is that, the other one is that, pedo curve of the hyperbola with respect to the center. And here is the pedo curve of hyperbola with respect to the focus. It's very fascinating because the pedo curve of a hyperbola turns out with respect to the focus, then you get a circle. How beautiful, you got a circle right there. Am I doing good? Okay, you got a circle right there. But when you have a pedal curve with respect to the center, then you get this curve, which is called lemniscate, okay, which is another famous curve, like figure 8 shaped lemniscate of Bernoulli, I believe. So you can go to my visual dictionary of spatial plane curves, go to hyperbola, click, and go down. Then you'll see the pedal curve section properties. Okay, so point-wise construction, optical property, pedal. Now, I'm not sure that's pronounced pedal or pedal. Actually, I don't know. You never read, you never hear, someone speak it. You have to be in a math circle too. But this topic, plane curve properties, is not a super popular topic in mathematics. It's not something they will teach you in school, in calculus courses. In calculus courses, all these are suitable, but usually they will cover hyperbola, ellipse, parabola, conic sections as elementary, but some of the other cissoid of Diakos, conchoid of Nicomedes, quadratrix of Hippias, they will not talk about it. They will, you might see it in exercise, like the exercise 51. There is this curve called quadratrix of Hippias, created by Hippias in 2,000 years ago by the Greeks. So how do you prove this property, using the thing you just learned, calculus? So sometimes you'll see that, but usually you will not learn about this. So similarly, for some of these spirals, Archimedean spirals, equiangular spirals, and convolutus and hypotrachoid, this is the most famous, known as spiral graph. They are used in dollar bills. You see, when you see a dollar bill, you'll see this thing going crazy. I learned it only last year, that the reason they put that there, this spiral graph, so-called, technically in math it's called hypotrachoid, okay? Hypotrachoid or epotrachoid. So there's several variations. Epotrachoids looks like that, and hypotrachoid looks like that. So the reason they put this on dollar bill is that it is very difficult to figure out, given the curve, it's very difficult to figure out the parameters to generate that curve. Therefore, if you are a counterfeiter, if you're gonna print money from scratch, your curve will be different. So that's why they put this in dollar bills. You see all the different currencies in US dollars, in other countries' money. So hypotrachoid. So these curves, these are all appropriate subject at the level of calculus. Okay, so if you are college students majoring in math, these are all good for you. Some of them cover algebraic geometry. They are objects of algebraic geometry, which is very advanced. Usually that's graduate level. Okay, but you can but it's easy to understand for beginners. You can understand what they are about. So anyway, so that's what these plane curves are. Okay, so you got sine and cosine. Look at these spectacularly beautiful graphics, which this one I created. I call it theory. Okay, and the Wolfram language code is right here. Copy it. Let's try to plot it. Okay, let me just show you. Cheers. You see how beautiful is that? This is typically called implicit plot. Super. Hello, the violator. So I bet you will never use Svarboard. It will end up in your bin. No, that's not true. Okay, so let me talk about that because a lot of people has been waiting for me to review this smart board. Let me digress a little bit. Okay, so a lot of people has been waiting for me to review. Where's my OBS? Review this fantastic advanced keyboard device with magnetic switches. It's not a normal keyboard. I haven't started to try it because it takes some time. Okay, so I put it there. It's right on my desk and it's connected. That means that reminds me I actually need to do it. But it's been over a year now. But however, that situation is common with me. Sometimes I have a subject that just sit there for sometimes a few years. But I will get to it, okay? So thank you for that comment. I bet you will never use it, so that makes me, I'm gonna try to use it. Take some time to learn and explore because that's kind of a big project for me, okay? I mean, on the other hand, you could say, well, I mean, it's been over a year and you haven't done anything with it. That's true, okay? But that's kind of common thing for me, common situation, okay? So can you explain flux in calculus, please? No, I cannot. I don't know about flux. What is flux in calculus? CALCUL. Maybe I can explain after I read it. Okay, so wait, where is the, okay, turn on the Grok, turn on I'm using the Brave search, which has a built-in artificial intelligence chatbot. So I highly recommend Brave search, brave.com, okay? And I highly recommend the Brave browser. I'm using the Brave browser for my Twitter here, okay? So I recommend it. Download the Brave browser or set your Google search, web search to the brave.com search engine. Just install a plugin. Search it, you'll find it, okay? So let's see, what is the flux in calculus, particularly in vector calculus? Flux is a measure of how much a vector field flows through a surface. Okay, a vector field flows through a surface. It quantifies the amount of a vector field passing through a given surface, okay, taking into account the strength of the field, the size of the surface, and their orientation relative to each other, okay? The concept of flux is often used to describe the flow of fluids or electric fields through a surface. Okay, I know what's a vector. I know what's a vector field, but they are doing it onto a surface, so that's the part I'm not sure I understand. Okay, so you can see there's a lot of tutorials these days on YouTube, on Khan Academy, on lots of places. So, but let me look up Wikipedia, okay, because I prefer, there it is, Wikipedia, the real thing. So can I explain flux? Pay me. How much you pay me for my explanation? Because my explanation, oh, fuck, I forgot to switch back, okay, because my explanation is, gives you the gist of things, so you avoid misunderstanding, okay? So there it is, flux. Flux describes any effect that appears to pass or travel, whether it actually moves or not, through a surface or substance. Flux is a concept in applied mathematics and vector calculus, which has many applications in physics. For transport phenomenon, flux is a vector quantity describing the magnitude and direction of the flow, okay, of a substance or property. You see, so the thing I don't know is that it's on a surface, so normally a vector field a vector field can be 2D or 3D or higher dimension, but let's think of 2D. So vector field is easy to understand. So you just have a plane. For each point, you have a vector. Okay, vector is basically just an arrow. So for each point, you have a vector. So you can see that point will move to what direction or how much by the magnitude. So when you have a vector field, you can plot it and you can kind of see the direction of flow, like wind. For example, if you check weather, you check weather map, then usually you will see a vector field. So let me just ramble, okay? So let's see, vector field, national and local weather radar, something. Okay, let's go there. Turn on JavaScript. Okay, so you got this. This is a contour plot. Okay, that's not a vector field, but can you see? You're gonna show vector field somewhere. You'll see it. Let's see. Let's look at this one. This is kind of not vector field, but anyway. I want to get back to parabola. So anyway, let's read. In vector calculus, flux is a scalar quantity defined as the surface integral of the perpendicular surface integral of the perpendicular component of vector field over a surface. Okay. Yeah, okay, I cannot explain it. Okay, so general mathematics definition, transport. Okay, so flux. So you see the key about flux, how they differ from a vector field, is that it's applied to a surface. So you got the vector field, but applied to a surface. But okay, so what does it mean? So you can see the graph gets complicated. Oh, okay, so now it shows visually, so now you can kind of understand. Okay, so it's actually right. So the blue arrows you see here are the normals, meaning that the blue arrows is perpendicular to the surface. Okay, now the red arrow is the thing you want. It's, I suppose it's called flux. The red arrow actually shows where on that surface at that point where the force or whatever is going. So these red arrows are the flux. The blue arrow is just perpendicular lines to the surface at that point. Okay. So, but what I mean, so I don't know the application. So, this is supposedly related to a lot of physics. I'm not too interested in physics, in the math for physics. So that's why this subject does not attract me. Okay, so general mathematical definition, transport. Okay, the field lines of a vector field. The field lines of a vector field F through surfaces with a unit normal n. Okay, that's the normal, that's perpendicular to the surface. The field lines of a vector field F. Okay, so this yellow line is the flux, I suppose. Of a vector field F through the surface with unit normal n, the angle from n to F is theta. Okay, so this is a perpendicular line to the surface at a point on the surface. Then you have another line that's a flux. So that this line makes an angle with the normal. So that's theta. Flux is a measure of how much of the field passes through a given surface. Okay. How much of flux is a measure of how much of the field passes through a given surface. F is decomposed into components perpendicular and parallel to n. Okay, right. So okay, F is the flux. Okay, so right, it's so this flux line, so this is perpendicular, normal. This flux line, it may point in anywhere. So, but this flux line can be decomposed into three vectors. Okay, one is the normal, the other two is parallel, the tangent surface to that point. Okay, so F is decomposed into components perpendicular and parallel to n, to the normal. That's right. Only the parallel components can contributes to flux because it is the maximum extent of the field passing through the surface at that point. Okay, the perpendicular components does not contribute. Okay, but they contribute the direction, don't they? So top three field lines through a plane surface, one normal to the surface, one parallel, and one intermediate. So one normal, one parallel. Okay, this F, you see this one, parallel, and intermediate, that's the flux. Okay, so bottom, field line through a curved surface showing the setup of the unit normal and surface element to calculate flux. Okay, so to calculate the flux of a vector field, red arrows. So this is a vector field on a surface. Okay. Okay, so I think so you get the idea. So does that help? Does that help your question? Where is the what? Did you just delete it? Why do you guys do that? Who asked that? Okay, that's kind of flux. Okay, that's related to. It's not So this topic flux is not. It's more about. It's more about mathematical physics. It's not mathematics. Okay, so I'm not too interested. The word flux came from Latin. Fluxus means flow, and fluere is to flow. Fluxion. This term was introduced to differential calculus by Isaac Newton. Okay. Flux describes any effect that appears to pass or travel through a surface or substance. Okay. Now you see the thing I don't understand, why through a surface? Because when you are talking about fluids or air, it's a 3D manifold, so it's not just the surface. So when is it useful? When you actually do talk about these things on a surface. Surface is just like a patch. Yeah, I don't know what is it used. So we can look at the application. Okay, so properties, quantum mechanics. Okay, so flux as a surface integral. Okay, surface integral is complicated. Electromagnetism. Okay, I don't know. SI radiometry units. Okay, yeah, I don't know. It's more physics related. Why do you delete the question? Colostomy Bag says, I just got a Mac and it's incredible snappy, even better than a lightweight distro on gaming PC. Yeah, Mac is very good. Yeah, especially when they came out with one so-called Apple silicon, you know. Anyway, let's go back to what we need to do. Okay, so let's go back to this pedal. Did I explain what it is? I didn't, I guess. So hyperbola, so you go to pedal. Oh god, we kind of rambled a lot. So you go to pedal, so you can see pedal explained there. Then there's a lemmascate of Bernoulli. Let's go to them. Pedal, lemmascate of Bernoulli. So when you have the pedal curve of a hyperbola of a rectangular hyperbola with respect to the center, then you get the lemmascate of Bernoulli, which is this curve, like an 8, infinity, the symbol for infinity. Okay. So let's see. Let me show you. Okay, so that's a Unicode. You see? Beautiful. Infinity, okay? So go there, describe character, then you can see the name of that character is infinity. There. Okay, so the function you want to call is describe character. Okay, so this is the power of Emacs. So this infinity symbol is kind of like this lemmascate curve. So, and you can see the properties with relations to rectangular hyperbola, and lemmascate is also a curve when you slice a torus. Okay, a particular torus. Okay, and there is linkage properties. Fascinating. So these curves are so many fascinating properties. Okay, close that. So let me go back to, so what is the pedal? Okay, so pedal curve is so pedal curve is given a curve. Okay, given a curve, you know, can be a sine, can be a circle, can be a line, or can be a parabola, or any. Given a curve on a plane, can you see me? Yeah. So given a curve on the plane, and with respect to a specific point on the plane, okay? So you got a curve and you got a point somewhere in the plane. Okay, given these two things, then you can define a thing called the pedal of that curve with respect to that point. So what you do is that for any point on the curve, let's say P, okay, so you got a point on a curve, how is it defined? So given a curve and a fixed point O, draw a line from O to any point P on the curve. So you have a line from O to passing the curve, okay? Then draw a line perpendicular to line OP and passing P, okay? Right. Okay, so repeat step 2 and 3 for every point P on a curve. The envelope of the lines is the negative pedal. Okay, so that's the negative pedal. So I want the positive pedal. So draw a line tangent. Okay, so let's see. Given a curve and the point O, draw a tangent at any point P on a curve. That's right. Yeah, that's right. Okay, so let me. Can I show you interactively? Yeah, I can. So let me do this way, okay? So let's paint. I want photo same sketch. Okay, given a curve, let's say that, and given a point, this is called pedal curve, okay? Okay, so given a curve and given a point, now you can have a pedal of this curve with respect to this point. Okay, so what you do is find any point P on the curve, any point P on the curve. Okay, so then for any point you got a tangent. In this case it looks like that. Then you want to find a point on the tangent such that that point to the O is perpendicular. So in this case it'll be a point like that there. Okay, let's call it Q. So you got that point. So for every point P on a curve, you draw a tangent, then you will find another point Q. Okay, that is such that Q, O, and Q is perpendicular to that tangent. Okay, so for every point P, you got a point Q. Now, the set of all point Q is the pedal curve of this curve with respect to this pedal point O. Okay, I hope that's interesting and clear. Okay, save it, close that. Okay, so that's what pedal curve is. Okay, now, so you can see some examples. So if you have a parabola, and then if you have the focus of the parabola as the pedal point, then the pedal curve of the parabola is a line. Fascinating. So that's what pedal curve, so there's so many relations. You got parabola, lemma sum of Pascal, then you got parabola with a different pedal points, you got several different curves. Then a circle, if the pedal point is on the circumference, then you got a cardioid, okay, which is very famous as well. So you got lots of these: cardioid, deltoid. Deltoid is particularly beautiful. If you put a pedal point on the cusp of the deltoid, which is like one of these pointed position, then you get a double folium. Okay, that's fascinating. Let's see if I got an example here. Pedal, deltoid, so many interesting properties. Okay, so let's see, pedal, there it is. So you see, if you have the curve, this curve is called trifolium. Okay, it looks like that. Okay, it can be generated by rolling circles like that. Okay, you see, just roll a circle, then you got this curve called deltoid. Now that deltoid has so many properties. Okay, so many properties, but one of them is pedal. So if you create a pedal curve with respect to one of these cusp, one of the corner, then the result is this three leaves. That's called trifolium. Okay, so it's incredible. Trifolium is this curve. Okay, that's one of the rose curve. Okay, so incredible beauty. Okay, in this mathematics. Do you guys see it? Do you guys understand what I'm saying? Is it interesting? Okay, so back to hyperbola. So let's quickly do these graphics and let it be that for today. Okay, so remember, go to Visual Dictionary of Plane Curves. You'll find all these interesting properties if you are college students focusing on mathematics. Okay, this is the heart of engineering and AI and technology and rocket science. if you're gonna build a rocket, you need to know all this, okay? So every time I see Elon Musk, our dramatic boss, Elon Musk, let's see, where is his following? Okay, so you can see Elon Musk. He's shooting rockets almost like every day, every week, every month. Okay, so you'll see these incredible achievements of rockets flying and landing. Like, I mean, one of the key issue today is that you want it to come back and land it so that you can reuse it again. Okay, where is my? Let's go here. Elon Musk. Okay, so there it is, Elon Musk. Okay, so go to his Twitter. So so this is Mars. Let's see. Let's show some. You see. Now this is incredible feat of mankind. Okay, that's incredible feat of mankind. Okay. So the issue today is that you want it to come back. Like in the past, you just throw away. Once it flew, you just throw away the booster, the engine, whatever. But because we don't know how to make it come back and land, but now we can. So this is literally rocket science, and Elon Musk is doing that like almost every month. You see incredible things happening. Elon Musk does a lot of things, so I don't know if it's possible. Maybe it's actually someone else do it, and at least he's taking some of the credit. But actually he knows things. Anyway, but this rocket is happening. Okay, that's for real. And in order to know all this, you have to actually know all this. This what we are talking about today, geometry. Okay, so let me quickly just finish that. Let me quickly finish this pedal thing. Okay, so I just want to quickly finish this. Let's see if I can do that. Search for pedal. Okay, so there is the pedal section. We're gonna update the graphics. So let's do it. Wolfram code. Okay, paste it here. Okay, so here's the code, and this part we don't need. This part we don't need. Yeah, let's just copy, paste that, make it comment, copy, paste that code, and what is the next one? Okay, copy, paste that, make a comment. I'm using Wolfram, Wolfram mod, so that allows me to code Wolfram language in Mathematica. I mean code Wolfram language in Emacs actually. So let me copy that, new notebook, paste it. Okay, so we're gonna work on here. Copy that. Okay, so we wasted. So we are doing this. Okay, so let's delete the semicolon because the semicolon suppresses output. Okay, now this paraplot we need to load it. Okay, so there. So we load it, And this hyperbola equation, we also need to load it. So okay, so actually, so we need to, let's define a variable, and let's define hyperbola. It's for my package, so let me get the package, get formulas. Okay, so formulas, WB, search for hyperbola. Okay, so this is the formula, this thing, copy it, close, defined here. Okay, so we define this formula, and this secant, this formula can be improved because secant function is even function. Because it doesn't matter. Anyway, let's not worry about that. So anyway, so you got the hyperbola formula defined. Let's make it more readable syntax. Okay. So this line and this line are equivalent. I just made it more readable. Okay, so you got the hyperbola, and this E is the eccentricity. Now highlight it. So this gets complicated. So paraplot, so this name change. This is actually not called paraplot. This is called, because I changed the name. It's called plane curve plot. Okay, so for every occurrence of paraplot, you need to change it to plane curve plot. Okay, wait. Yeah. What? There. Okay. So we load the package, we clear some parameters, local variables, we define the hyperbola formula, and okay, so yeah, then we define some of these. This actually we don't want the first. Okay, so let's highlight all occurrences. And you see, this is 30 years old code. 30 years old code. So I'm doing some cleanup because after 30 years, there's a lot of changes in Wolfram language. So I don't want this first there, and but you put the first there, and okay. So let's do some, and this part, parametric plot, pi over 2 to pi, half pi, 1.5 pi, 2 pi, so this is 2 pi here. Okay, so let's remove that. And display function we don't want because that's changed. So let's just plot this part. Okay, let's see. There's a lot to do here. There's a lot to do here. So save this as untitled. Okay, save it. So paste this. Wait, what? Okay, so we need to copy that, and open a new, paste, shift enter. Let's see. Successful. Okay, so what about this part? So let's see, 3.14 4.16. That's basically pi. And so let's put that, paste it here, shift enter. Beautiful, successful. Okay, so we got that. Now can we just change this to pi? Paste, run. Beautiful. Okay, so let's remove those tabs. Okay, 100 red wine to soothe my soul. So we are almost 1 hour. Okay, so that still works. That's good. And what about this part? What does this part do? Pi. Okay, pi. Okay, there is, you got some problem. Now is it because this thing why? Because pedal, we haven't defined pedal. Yeah, so okay. So anyway, let's wrap this up. Okay, so we got these two images we want to replace, and we can do that. So yeah, so the second image we haven't done yet. That's supposed to be this one, but now we got an error because this function is not found. Yeah, that function is not found. That's why. But this, but let's just do this one. Okay. Now, why are there two of them? What's the difference? Oh, because every time I'm using random color. Okay. So these two are exactly the same, you know. So this one is using pi, and this one is not. So delete that. But anyway, so this is a picture we want. Copy it. Okay, and we can replace that image. Okay, let's do it. Put this back and add the image, move the image here. Okay, well, that's actually, that needs to go to Xar Talk Show. So Xar Talk Show there, and put the image here. Okay, and relocate it to Xar Talk Show and rename it pedal curve. Okay, and update this line. Do it, show in browser, Xar Talk Show. There is what we talked about. Now go back here, close that, go back here. This we delete. Now move the image again. Here is the pedal. Okay, rename it. Fantastic. Show in browser, search for pedal. Okay, fantastic. Now we just need to delete this one. Okay, and here we copy it. So delete this image because now we got a much better one. Let's put it side by side so we can see. Showing browser, refresh, there it is. Okay, yeah, beautiful. So yep, much better. So now we want to delete this image. Before we do, let's go to find. We want to make sure this image is not linked from other places. So paste it there and do search. This is a Golang code, which is basically doing grep. Okay, that's it for today. Thank you guys for watching. Okay, so there it is, the result. Not yet done. Fantastic. But that's it for today. If you like my stuff, go to xali.info and go to the bottom, xali.info, okay? So code xali.info, go to the bottom, there is Amazon, Patreon, and PayPal, okay? Pay me $100. So this search is still running. Let's look at some of the Elon Musk, okay? That's it for today. So let's go back here. What did I talk about? Close that.
Wind chills as low as minus.
Close that. Flux. I have no idea what is flux. Okay. Showing browser. There. Just say flux. Okay, bye guys.